Have you ever pondered about the mysteries of the universe? What secrets do black holes hold within their dark, unfathomable depths? Imagine, if you will, an entity so powerful, so dense, that not even light, the fastest thing in our universe, can escape its grasp. This is a black hole, one of the universe's greatest enigmas. These celestial bodies are regions in space where gravity is so intense, so utterly overwhelming, that it consumes everything that dares venture too close. Their immense gravitational pull compresses matter into a point of infinite density known as a singularity, creating a region from which nothing can escape. This includes the very essence of light itself, which is why we call them black holes. They are invisible, yet their presence can be felt throughout the cosmos, influencing the motion of stars and galaxies. So black holes are indeed fascinating, aren't they? But what makes them even more intriguing is how they relate to the theory of relativity. Einstein's general theory of relativity may sound like a mouthful, but let's break it down into simpler terms. Imagine a trampoline. When you place a ball in the center, it creates a dip, right? Now think of that trampoline as the fabric of space and time, and the ball as a massive object like a star or a planet. The dip that the ball creates, that's what we perceive as gravity. Before Einstein, our friend Sir Isaac Newton thought of gravity as a force that pulls objects towards each other. But Einstein, being the revolutionary thinker he was, said, hold on a second, what if gravity isn't a force at all? He proposed that what we perceive as gravity is actually the curvature of space and time around massive objects. So let's go back to our trampoline example. If you were to roll a smaller ball towards the larger one, it would naturally fall towards it. Not because the larger ball is pulling it, but because it's following the curved path set by the larger ball. That's essentially what Einstein's theory of relativity tells us. Massive objects like stars, planets, and especially black holes warp the fabric of space and time around them, creating what we perceive as gravity. Now, when we talk about extremely massive objects like black holes, they warp space and time to such an extreme that they create what we call an event horizon, a point of no return. Anything that crosses this boundary, even light itself, can't escape the gravitational pull of the black hole. This revolutionary idea changed our understanding of the universe fundamentally. It told us that space and time are not separate entities, but are interwoven into a single continuum known as spacetime. It's a bit like a cosmic dance, where massive objects and the space-time fabric move in sync, guiding the motion of everything in the universe. So remember, according to Einstein, gravity is not a force pulling objects together. It's the warping of space and time around massive objects. Now, you might be asking, what does this all have to do with black holes? Well, it's quite fascinating. Black holes are a direct prediction of Einstein's general theory of relativity. They are the ultimate conclusion of what happens when matter is compressed into a tiny space, causing an intense gravitational pull. Imagine spacetime as a stretched-out rubber sheet. When you place a heavy object on it, like a bowling ball, it creates a dent. This dent represents the warping of spacetime. Now, if that object is incredibly heavy and incredibly small, like a black hole, it would create a deep, dark pit, deforming the rubber sheet to an extreme degree. That, my friends, is the essence of a black hole. At the very center of this pit lies what we call a singularity, a point where the laws of physics as we know them cease to function. Here, the gravitational pull is so immense that it warps space and time to an infinite degree. Around the black hole, there's a boundary called the event horizon. Think of it as the edge of the pit. Once you cross this point, there's no coming back. The gravitational pull is so strong that not even light can escape, hence the name black hole. Now here's where things get interesting. The closer you get to a black hole, the slower time moves. This is due to the intense gravitational pull of the black hole. If you've ever heard of the twin paradox, it's a similar concept. One twin travels near a black hole, while the other stays on Earth. When the spacefaring twin returns, they would be younger than their Earth-bound sibling. It sounds like science fiction, but it's just relativity at work. In essence, black holes are the universe's finest demonstration of Einstein's general theory of relativity in action. They are real-life laboratories where we can study the extremes of physics and the very fabric of the universe. So, we've learned about black holes and Einstein's theory of relativity, but what does this mean for us? Well, Both black holes and Einstein's theory of relativity are key to our understanding of the universe. They've reshaped our perception of reality, revealing a cosmos that is far more mysterious and fascinating than we ever could have imagined. Black holes, these enigmatic cosmic entities, are not just fascinating celestial objects. They are fundamental to our understanding of the universe. They challenge our perception of gravity and spacetime, pushing the boundaries of our knowledge and understanding. And then there's Einstein's theory of relativity. It's not just a theory. It's a blueprint of how the universe works. It explains how gravity operates, how time can bend, and how the fabric of space itself is woven. It's a theory that has helped us understand the very nature of existence, from the smallest atomic particles to the vast expanses of the cosmos. One of the most exciting developments in this area is NASA's black hole visualization. This groundbreaking project allows us to witness the effects of a black hole's warped spacetime. It's like stepping into a cosmic roller coaster, a thrilling ride that takes us to the very edge of reality. We can experience the surreal phenomena that occur near a black hole, such as the distortion of space and time and the bizarre effect known as spaghettification. This visualization acts as a bridge, connecting the abstract world of theoretical physics with the tangible reality we live in. It brings the mysteries of the universe a little closer to home, making them more comprehensible and less intimidating. These advances in our understanding of black holes and relativity are not just academic exercises. They hold the potential for future scientific discoveries and technological breakthroughs. They could lead to new ways of harnessing energy, novel methods of space travel, and even a deeper understanding of the origin and destiny of the universe. As we continue to explore the cosmos, black holes and Einstein's theory of relativity will undoubtedly guide us, serving as cosmic compasses in our quest for understanding.